This week, we're excited to welcome Richard Moulds of Whitewood Security back to the Security Weekly Network, and he'll be here on a very focused discussion on the recently publicized ROCA crypto bug. In the news, Tanium announces a new asset module. Carbon Black forms a partnership. Stackflow is in the news. Elusive Networks as well. So stay tuned. Enterprise Security Weekly is coming up. This is Security Weekly, for security professionals, by security professionals. Broadcasting live from G-Unit Studios in Rhode Island, it's the show where we talk security vendors and aren't afraid to name names. It's Enterprise Security Weekly. The teleprompter now has artificial intelligence, Doug, and updates itself. It's awesome. This week, and talk about them as it relates to enterprise security. You're gonna do great.
I think that people think that you and I talk like every day at night. You know, It's like, hey, what are you doing? It's kind of a bit of an exhausting week, and I think that we noticed that a little bit in the stories for this week as well.
Logarithm's Netmon Freemium delivers real-time network visibility to quickly identify emerging threats in your IT environment. Netmon Freemium is a free commercial-grade network forensics and traffic analytics solution. You can use Netmon Freemium's powerful capabilities to search against all observed network traffic, identify abnormal traffic patterns and application usage, and quickly analyze full packet captures. Take the first step towards real-time network visibility. Visit logarithm.com/freemium to learn more and download it today. Are you worried about PCI compliance? Does your development team understand or care about security? Are you ready to face a breach of your customer sensitive data? See the worst that can happen before it does. Black Hills Information Security can help you help management see the future. Email consulting@blackhillsinfosec.com to find out how a web application penetration test can mitigate the risk before you go live. Welcome, everyone, to Enterprise Security Weekly. This is episode 66. Yes, 66. It's October 18th, 2017. I'm your host, Paul Astor, of course, recording live in G-Unit Studios. Very excited about today's show, as always. On the lines via Skype, Mr. John Strand joins us. John, welcome to the show.
Hey, very happy to be back, finally, after being on the road for far too long.
Yes. Good to have you back, John. A couple of quick announcements. itpro.tv/enterprise security. Make sure you use the code ES30. Try it free for 7 days. Check out the supervisor portal so everyone in your organization can take advantage of their awesome on-demand live video, full transcript recorded for each training module. Take advantage of all that. Visit our fine friends at itpro.tv. I'm doing a Kung Fu webcast as well. If you've missed my talk, everything I need to know about security I learned from watching Kung Fu movies, I will be delivering that next week. You can subscribe to the webcast, register for the webcast at securityweekly.com/Kung Fu, where I will talk about some of the parallels between Kung Fu movies and security.
And there are far too many of them. I was shocked.
Actually, I have to cut it short because the talk kind of runs long, which is pretty funny. So that'll be a good time. I have given that talk several times this year, so if you happen to have missed it, you can check it out. And I'm retiring it after this year, so we're recording it for posterity. So make sure you register and check that out. I'd like to introduce our special guest for today, Richard Moulds of Whitewood Security. He is the king of Entropy, as he dubbed it, which is awesome. Richard, welcome to the show.
Hi, Paul. Nice to be back.
Yes, nice to have you back on our network. And we brought Richard back specifically because of this ROCA crypto bug that has been publicized recently this week, and my inability basically to explain it as well as, well, not as well as many people, and certainly nowhere close to as well as Richard can explain it. Richard's been on the show before talking about the importance of entropy, the importance of randomness, and some of the underpinnings of this vulnerability revolve around not having enough randomness. So I thought, who better to bring on the program to talk about this crypto bug than Richard? So, Richard, I want to start with the name of the bug is the return of the Coppersmith attack. And so yes. I guess we should start with what's the Coppersmith attack?
So the Coppersmith attack's been around for a while, and it's been a mechanism for cracking asymmetric cryptography, which is where you have a public key and a private key. But in the past, it's relied on there being some basic knowledge of what's been going on at either end, or having some insight to some of the keys that form part of the algorithm. This is called, I guess, return to coppersmith. We don't quite know exactly how it works yet because the discoverers haven't discovered them yet. That happens at a conference in a couple of weeks' time. But it allows you to calculate the public key in the private key, just knowing the public key, so without any need for any background information at all. So when we think about asymmetric crypto, you've got a certificate and a private key. You can determine the private key directly from the certificate with no other knowledge.
Yeah, that's kind of frightening. And so now I've been told that the amount of time it takes to derive the private key from the public key greatly depends on your key length. Can you speak to that a little bit?
So yes, it does. So as you know, when you use cryptography, the amount of bits in your key determines how hard it is to break the key. So most crypto systems, or at least asymmetric RSA algorithm crypto systems, are using either 1024 bits or 2048 bits, and even 1024-bit keys, are incredibly difficult to break without the advantage of this latest flaw. They are talking about it being crackable in 15 minutes or less. So, even you might get lucky and do it in 4 or 5 minutes, but the worst case is 15 minutes. And for 2048-bit keys, 15 or 16 days of attack, which sounds like a long time, but if you're going after a piece of information you particularly care about, then that's a massive improvement on your chances of breaking this stuff without this vulnerability. And one of the downsides, I suppose, of the vulnerability is that you can paralyze or parallelize the compute necessary to break these keys. So the more CPU cores you throw at it, the faster it goes.
Now, there were some calculations, if you were using Amazon Web Services, that it could cost anywhere between $20,000 and $40,000 to break the 2048-bit key. Do you, in your opinion, are those estimates pretty accurate?
I mean, until we know exactly how the attack is performed, then it's difficult to estimate. But I guess they seem plausible figures. As I say, I think this vulnerability has actually been handled in the correct way. This isn't a bunch of researchers that have come out and, told the world the sky's falling. This was discovered 8 months or so ago, and we're only hearing about it now because the vendors have got patches and solutions to fix it. So, that's the right way you should talk about security flaws: is warn the people that can fix it first, give them a chance to fix it and get their ducks in a row, then tell the public. And even then, don't tell people how to actually exploit the vulnerability. So we now have 2 weeks for people to download the patches and change their keys before the actual attack method is disclosed. And in principle, the bad guys can start trying to find the laggards out there that haven't changed and updated.
And now, it's not every key in existence, correct? It's only a certain subset of the keys that exist today.
Yeah, and this is the big irony of it all. It actually only affects keys that were generated in cryptographic hardware, so not software generated. Unfortunately, so these are the people that actually try to do it correctly. Generating keys in software and storing and managing keys in software is always a little bit up for grabs. So the really sensitive keys that are out there, the really valuable data, the real mandated stuff, is done in hardware, either on smart cards or in hardware security modules, or in special chips called TPMs, trusted platform modules. And these things are built into the motherboard of most laptops and most computers and servers. And they have the specific job of generating good keys and physically storing keys from theft, anti-tamper. So unfortunately, this vulnerability affects smart card generated keys, TPM generated keys, and potentially HSM generated keys. So it's unfortunately biting the people that actually tried to do it correctly from the outset.
So one of my concerns about this is, one, how do you patch this effectively? And then two, whenever you do try to patch it, does it actually, and you're trying to patch it in the software on the operating system, does it actually undermine the core goal of having it on the TPM module itself, or the Trusted Platform module itself?
I don't think so. No, it's the use of hardware to generate keys and store keys is still perfectly sensible and recommended. When you generate asymmetric keys, public and private key pairs, it involves the use of prime numbers. Unfortunately, generating prime numbers and testing a number for its primacy can take a long time, and it can be a real drain on resources. So there have been some algorithms created over the years to accelerate that process of finding prime numbers, which is a software algorithm. And the issue in this vulnerability is that algorithm was flawed, and that algorithm was loaded as a library onto a variety of these hardware chips. So I think if people upgrade the library on the chip, then the system is restored, back to its full strength. So the concept of using hardware isn't broken. The chips themselves, provided they can be updated, are fine. It's just a question of getting this prime number finding algorithm fixed.
Okay, and then continuing with the patching idea, we have patches out from Lenovo, we have patches out from Microsoft, we have a number of different patches that are coming out in this area. And you had mentioned before the show started that a major concern with all of this is the fact that there's a bunch of Internet of Things that may not be so easily patched.
Well, that's right, and this is embedded technology, right? These are the company in question here is a company called Infineon, a German company that were one of the innovators in TPM chips and smart cards years and years ago. The trouble is, of course, who knows where these chips are actually installed? These are embedded devices. This isn't software that the user installed themselves. This is not something you downloaded. This isn't a chip or a device you went out and purchased. This is something maybe in your IoT device. How do you know? So I think figuring out what systems need to be patched in the first place becomes your bigger challenge. And then, as you say, because these are embedded applications, the pathway to updating the firmware on a single device in your machine, that pathway may be an easy one, or it may be an incredibly difficult one. Patching in the context of IoT is already sort of notoriously difficult. And and this might really prove the point, because this is going to have to be done on a mass scale.
Yeah, well, there is a website that was set up. I'm not sure if it's by the actual researchers that discovered the vulnerability or another third party. There's a website set up that you can put your public key, not your private key, your public key into the website, right, and it'll tell you if it was generated with one of the chips that was using that flawed library. Is that something you recommend that people do, Richard? If you can get hold of your public key, yeah. I mean, that's... like I say, this vulnerability has been dealt with, very well, by the book. So yeah, I think those tools have been put up by the research team that found the vulnerability in the first place. That's great. Finding your public key for your website is easy, because that's something that's actively managed. But the authentication public keys and the signing public keys and the encryption keys that you might use, for example, hard drive encryption on your laptop. I mean, finding that stuff and then getting it to this website is not a simple task. And it's an incredibly manual task, and it relies on you knowing your way around, your operating system and your hardware pretty well. So it's a great tool, and it's very rare in these types of situations you have something to actually go test to see whether you're vulnerable. But actually doing it on a practical scale, might be quite tricky. It exposes a really interesting aspect to this vulnerability, which is, I think, what really, really makes it scary, in that you can tell just by looking at a site or at a certificate whether or not it's vulnerable. When we've heard about crypto vulnerabilities in the past, particularly when it comes to key generation, there's no easy way to spot the weak site from the strong site. So although it might be incredibly weak, if the attacker hasn't got a clue which of the sites that are weak, then they sort of have to be speculative and try everything. But with this particular vulnerability, you can grab a certificate and go test if it's weak and then go after it. So this is this is like putting a flag on all the banks that have left their vault door open. Now, some of the keys can be generated right on the individual devices, or like YubiKey, you can generate your key pair right on the actual device. That's right. I mentioned that's in the business journey of generating entropy. Like, how do you get more, if the problem stems from inherent not having enough entropy. Like, how do you get more entropy on something of a little tiny little dongle that's going to generate my keys?
I missed most of that, Paul, because my connection froze. Could you just run through the question again?
Sure. So on a YubiKey, it's a hardware-based device that it can actually generate those keys. If the problem stems from entropy or there are other entropy problems, how do we get more entropy on a tiny little dongle like that to generate secure keys?
Well, this flaw doesn't stem from lack of entropy. I mean, there are plenty of examples where keys have not been random because of lack of randomness and entropy. This is a flaw in the algorithm. So this is the algorithm that takes random numbers and tries to find prime numbers, which it could then use to make keys. So the flaw is not a result of lack of randomness. It's in trying to cut corners to make the process of finding prime numbers more CPU efficient. So it's an algorithmic problem, not a problem with the RSA encryption algorithm itself, but with the mechanics of trying to find these prime numbers, which is one of the huge bottlenecks in generating keys. So
and isn't that ultimately, whenever we're talking about crypto, Schneier said it best. I think you'd never really attack crypto directly. You always attack the implementation of crypto, like how it's being used, how it's being implemented, how things are being passed, and so on.
Yeah, that's exactly right. So it's very rarely the algorithm that gets broken in any of these situations. It's almost always around the keys. Where do these keys come from? How well were they stored? And who has access to the keys in the first place? In this case, it's all about how the keys were generated. When we think about entropy and random numbers, we think about guessing keys. In this case, it's even worse because you can just simply go calculate keys. So I think when we spoke last, we talked about the threat of quantum computers and the concern that when a quantum computer comes along, it can simply calculate the private key from any public key. So in many ways, this vulnerability is almost a dry run for the issues that we'll face when a quantum computer comes along.
What are some of the challenges in updating the software on something like some of these hardware-based tokens? Like, are some of the logistics, like basically everyone has to go either get a new token or undergo some process to update the software on their tiny little token, which probably doesn't have like an Ethernet port or Wi-Fi in it?
Well, and it's even worse for smart cards. This is the same technology fundamentally is used in smart cards as it is for TPM chips and USB tokens. So, for example, they were talking about half of the citizen ID cards in Estonia being vulnerable. So now, these are things you've got to physically go and probably replace all of these cards. So if you've issued, potentially millions and millions of cards, and these could be cards that you use to sign documents. These could be cards that you use to get access to buildings. Obviously, government employees carry around their CAC cards to get into buildings and get into computer systems. So this may well come down to it being easier just to simply reissue the card than to try and update the firmware on the card.
Right.
And that's a very expensive process. That's physical, right? It's $10 a card. That's taking pictures. That's putting things in the mail. That's having people come to HR and get cards reissued. That's
and validating.
That's a painful process.
Yeah, and validating that person should be issued the correct card. That's a logistics issue for sure. John, more questions? Well, sorry, go ahead, Richard.
I was going to say,
go ahead, Richard.
If you're generating new key pairs, one of the bugbears of any PKI system, we're talking about public key infrastructure here, the system that generates these certificates, is revoking certificates. And the bigger a PKI gets, the more certificates have been issued. The bigger problem you have of managing all the certificates that have been revoked. So in this case, if we have to do a mass key generation or regeneration across our population, we may be revoking most of our certificates, which just compounds what's already one of the Achilles heels of any PKI-based system.
Fantastic. Was there anything else that you wanted to comment on this particular attack, Richard?
I think that I think the point about quantum computing is interesting. I think this is in many ways a dry run for what will happen when quantum computers shows up. But I think if we sort of stand back, the bigger picture is that more and more data is being encrypted. So we've got GDPR, the data privacy mandate in Europe coming along, and we've got data breach disclosure laws in the US. I think somebody said I read somewhere that 50% of the internet is now encrypted, and Google have started talking about actually downgrading websites from a search engine optimization perspective if it's not an HTTPS connection. So, there's a real commercial incentive to encrypt basically all data and encrypt all traffic on the wire. And as crypto becomes more ubiquitous, there will be a lot more research into the finer points of the implementation and deployment issues around crypto. So I think I'd expect to see more of this coming along in the future. And I think I think what it serves to illustrate is sort of crypto's is an all or nothing type technology. If the key's secret, then crypto's really sound stuff. But as soon as that key becomes known, then basically all bets are off. If you're using it for encryption, then that data is instantly available. And worse still, and we haven't really talked about signatures yet, but if somebody can get this private key, then they can issue software that appears to be authentic and can't be proven to be not authentic. So that means, that if people can start faking signing keys for code, then other software patches, not the patch to fix this problem, but a whole bunch of bogus patches, potentially containing malware and other gremlins, could be pushed into systems as authentic patches, but in fact are malicious patches. So I think there's a cascading issue here that will get people thinking not just about data, but about document signing and code signing, and that really gets us to think about the issues of IoT, which is where, of course, issues like code signing become just a massive and essential part of the problem at scale.
Yeah, it's potentially a very sneaky attack. We talked about the Wi-Fi attack that was happening, the crack attack, and this ROCA attack or attacks on any of the key infrastructure allows for what you're describing, for like very sneaky and stealthy style attacks that allow attackers to permeate into systems and maintain a relatively low profile.
Yeah, and I think that's the key word, is infrastructure. So yes, you should be worried about your own data and your own internet connections, SSL connections from your own laptop. But this takes on a whole new dimension when you think it can be used to, essentially disrupt software delivery and create, if you remember your Harry Potter, create an invisibility cloak for essentially illicit and malware-ridden patches. So this is a way of really messing with the infrastructure, not just stealing data.
Fantastic. Richard, thank you so much for appearing on Enterprise Security Weekly today. It was a great discussion, and we thank you for your knowledge and insights.
Great pleasure. Thanks a lot.
With that, we're going to take a short break, come back, and talk about the enterprise security news, so stay tuned.